Right, welcome internet audience. I'm a professor here at the University of Pennsylvania. My name is Aaron Roth, and I'm gonna talk to you for the next hour about ethical algorithms. You can say hi before I put on the slides. Okay, so let's begin. In just a second. Apologies. Okay, so there are two sort of important ethical issues that have arisen in technology, I'd say, over the past decade. These are things that both arise when you're applying techniques like machine learning to human beings, either using data gathered from human beings, about people, or when using machine learning to make decisions that affect people's lives. Okay, there's more than two of these issues, but the two that I want to focus on are privacy and fairness. Okay, these are related, but at a sort of very different stage of technological development. Okay, so in particular, what I want to talk to you about first is privacy, and I want to use this as a case study in which, we've got a success story. We've got a, well understood by now, rigorous mathematical approach for thinking about privacy. It's differential privacy that has made the transition by now successfully from the academy to broad use in both industry at places like Google and Apple and the US government. The 2020 US Census is going to be conducted subject to differential privacy. And this is a success story of a sort of very formal definitions-based approach to trying to understand exactly what the problem is and how we want to solve it. Okay. Now, much more recently, there have been, widely publicized concerns about fairness in machine learning, and we'll talk about that quite a bit. But here, people are thus far not even clear on what we want the definitions to mean. Okay, so fairness is really an emerging area of concern. It's where privacy was maybe a decade ago, but still, I think that, as we'll see, privacy can, the success that we've had with differential privacy can give us a promising way forward for how to deal with this. And I'll tell you about, some of what we know so far. Okay, the underlying theme is that although these are sort of both social issues, ethical issues, we can approach both of them rigorously. And in both of these fields, thinking about privacy and fairness, what we really have to manage are trade-offs. So, before I talk to you technically about what we might mean by privacy, let's just go through a couple of case studies in which things have gone wrong. Okay, I want to sort of convince you that privacy is easy to get wrong. So some of you might remember the Netflix challenge. This was a competition that Netflix hosted back in 2006, so more than a decade ago now. And the idea was pretty simple. They had some baseline recommendation engine. It was a collaborative filtering engine, but they wanted it to be better. And so they decided to host a competition in which they would release a large data set of movie review records of their customer base, and they would challenge the public, you, to develop an improved recommendation engine. And they had particular metrics, and they offered $1 million prize to the first team that could improve over the baseline of their existing algorithm by more than 10%. Okay. Now, of course, in order to run a competition like this, you've got to release data, and they did. And they were aware that there were privacy concerns around movie rental records. In fact, in the United States, movie rental records are protected by law to a surprising extent, which was the result of Robert Bork's confirmation process to the Supreme Court back in the 80s when the New York Post published during the confirmation proceedings his movie rental records. Okay, so they released this data set. It was you can think of the data set as being a big table in which the rows were, their individual customers, the columns were movies, and the entries in the table corresponded to, well, one, whether the customer watched that movie, two, how they rated it on a scale from 1 to 5, and three, the date at which they rated the movie. Okay. So they anonymized this data set by removing the names of their customers, okay, and just replacing them with random numerical identifiers. Okay. However, shortly after the release of this data set, a team of computer scientists who were at UT Austin at the time figured out that it was actually pretty easy to de-anonymize this data set, to reattach names to these supposedly anonymized records. Okay, and the way they did that is they essentially just cross-referenced the movie review records from the Netflix dataset to the publicly available set of movies that had been reviewed on IMDb with people's names attached. Okay, it turned out that by cross-referencing these two sets of records, you could get partial matches and re-identify a large fraction of people in the Netflix dataset. Okay, so you might wonder, by the way, why this should be considered a privacy violation if people were publicly reviewing these movies on IMDb. But the thing is that you might review all of the movies you watch on Netflix because you want better recommendations, but only review the ones on IMDb that you're not embarrassed to tell people publicly that you've watched. In fact, this was the basis of a class action lawsuit filed against Netflix as a result of this competition, in which an anonymous complainant, Jane Doe, asserted that her Netflix movie rental records would reveal her sexuality and that this would cause her issues with her employment. So Netflix settled this lawsuit for an undisclosed but presumably large sum and canceled the second Netflix competition. Okay, so this is to say that doing simple things like just removing people's names, it's not enough to protect privacy. Let me just go through one more slightly more surprising example. So human beings, people like you and I, have very similar genetic information. My genetic code shares 99% of the information that yours does. However, there are certain places in our genome where my genome is different than yours. In particular, there are positions in our genomes called single nucleotide polymorphisms, where some people have one set of base pairs and other people have another. Okay. So one popular large-scale use of medical data recently has been to run what are called genome-wide association studies, GWAS studies. And the way these work is at a high level pretty simple. Okay, you gather a bunch of people who all have some disease, say pancreatic cancer, and you sequence their DNA. Okay, and then you record for each of these positions, these single nucleotide polymorphism positions in which people's genomes might differ, just what fraction of the people in your population had the majority value for their base pair and what fraction had the minority value. Okay, there's millions of these positions, so you get a big vector of numbers, and the idea is you want to compare this set of numbers to the set of numbers you would get doing the same computation on some healthy population, and the idea is you want to find particular genomic markers that are, for example, indicators that someone might develop cancer. Okay, so these are valuable data sets, and when they were first arrived at, they were made public. Of course, even though people worry quite a bit about the privacy of medical data, this kind of aggregate information was viewed as safe because all that was being released were averages. It was numbers that said sort of, in this particular position in the genome, 26% of our patient population had the majority base pair, things like that. So that seemed safe, but it wasn't. It turned out that shortly after these data sets became public, it was discovered that there were simple statistical tests that could, with a high degree of accuracy, figure out whether a particular person was in the patient population that had been used to compute these statistics or not. Okay, and the idea was actually pretty simple. If I, for whatever reason, have access to your DNA, then what I will find if you were in the patient population was that in each of these positions in which our genomes might differ, the base pair that you have in your genome will be slightly correlated to the average of the patient population because you were in it. The correlation will be very small, but it turns out that because what's published is millions of these statistics, that these small correlations can add up, and the result is I can be highly confident that you were either in the study or not. Okay, and this can be a serious privacy violation because if I learn that you were in the study, this means that you've got the disease that the study was about, say pancreatic cancer. Okay, so this was shocking at the time to the medical community, and again had real implications. In particular, the NIH immediately removed from the public domain all of these statistical summaries of these GWAS data sets, which obviously has serious impact on the progress of science. Okay, so we can go through examples of cases in which privacy has gone wrong, but if we want to think precisely about how we can design algorithms that are going to somehow guarantee privacy, we've got to we now have to define what we mean exactly by privacy. Okay, so we've learned a couple of things from these examples. In particular, whatever privacy is, it's not accomplished by just removing personally identifiable information, things like name and zip code and age. And maybe a little more surprisingly, whatever privacy is, you don't get it just by releasing aggregate statistics. Okay, so instead we have to think a little bit harder about what we might mean really when we use the English word privacy. Okay, so let's give it a shot. Here's one attempt. Maybe privacy is about promising people freedom from harm. Okay, so we might say that an analysis, some machine learning algorithm we might run on a particular data set is private if the data analyst can learn no more about some individual, say Alice, in the data set after the analysis was run than he knew about Alice before the analysis was run. Okay, so this is sort of a sensible sounding thing, that we shouldn't be able to learn anything at all about any individual in the data set from our aggregate analysis of the data set. Okay, that sounds sensible, but there's a problem. Okay, consider the following scenario. Suppose that it turns out that Alice is a smoker, and an insurance company knows this fact. I mean, whether or not you smoke is generally publicly observable. And now suppose some scientific study is published that for the first time reveals that smoking and lung cancer are correlated. Maybe even smoking has a causal relationship to lung cancer. Well, the insurance company learning this fact for the first time and also knowing that Alice is a smoker now increases their belief that Alice might develop lung cancer and so might raise her insurance rates. Right, and so Alice has really come to some quantifiable harm. Her insurance rates are now higher. And so we should think about using this example as a case study, a thought experiment. Do we want to consider this a violation of Alice's privacy? Okay, so it's something we could discuss, but there's a couple of good reasons to sort of want to not call this a violation of Alice's privacy. So first of all, if we're going to go ahead and call this kind of thing a violation of Alice's privacy, then we're going to run into bad news. we're going to find that actually, privacy is inherently at odds with conducting any kind of science, right? Like this is trying to figure out some general population-wide statistic, a basic fact about the world, like that smoking and lung cancer are correlated, is exactly the kind of thing we want to be able to do with data. And if we're going to label an example like this as a privacy violation, then sort of straightforward to see that there's nothing, there are no non-trivial insights you can get from data at all that cannot be determined to be privacy violations. That you can formalize that. But if you think about it, there's also a pretty good philosophical reason to not want to label this kind of example a privacy violation, because it was possible for us to learn that smoking and lung cancer were correlated without ever having looked at Alice's data. We could learn this from a medical data set that didn't include Alice, right? Because this is a general fact about the world. The conclusion will be true and will hold whether or not Alice's information itself was in the data set we analyzed. Okay, so if there's some fact about the world that I can learn by going off and examining the world, never looking at Alice's data, and engaging in some introspection, it would be sort of strange to call that a violation of Alice's privacy. So let's give another attempt at defining what we mean by privacy. Suppose we said something very similar but different in a crucial way, that an analysis of a data set should be private if the data analyst knows almost no more about Alice after the analysis is conducted than he would have known had he conducted exactly the same analysis on an identical data set but with Alice's data removed. Okay, so let's reflect for a moment on how this definition differs from our first attempt. There's two ways. So the small difference is that rather than saying the analyst knows no more about Alice after the analysis is conducted, we've hedged a little bit and we've said almost no more. But the crucial difference is that rather than comparing the counterfactual worlds in which A, we ran the study, and B, we didn't run the study, how much we learned about Alice because we ran the study, instead we're now comparing two different counterfactual worlds, in both of which we ran the study, but only in one of which was Alice's data actually in the data set. Okay, so this is trying to quantify not what we learn about Alice as a result of disclosing some fact about the world, like that smoking and lung cancer are correlated, but instead trying to zero in on whether that fact that we learned was a function of Alice's data or not, whether we learned it because Alice's data was in the data set. And this turns out to be a very important difference. And this is the basis behind what's called differential privacy, which some of you might have heard about. Okay, so let me quickly tell you what differential privacy is, and it's a property of an algorithm. Okay, differential privacy is a property of a randomized algorithm. And think of these algorithms as taking as input a data set, which is a collection of records, each of which belongs to some person. Okay, then it, does something to this data set. It does some computation. The computation is randomized, and so in the end, it ends up inducing some probability distribution over its outcomes. If the algorithm is differentially private, then what that means is that if I run this exact same algorithm on a data set that's almost the same, but differs in that I've changed one person's data in some arbitrary way, then the algorithm should have almost the same behavior. In particular, it should induce almost the same distribution on people's outcomes, almost the same distribution on outcomes, where almost the same is something that is quantified in a very particular way. Okay, so let me give you the sort of formal definition, but if you're scared of math, don't worry about it. The particulars here aren't that important. Okay, so let's say that two data sets are neighbors, D and D prime are neighbors if they're almost exactly the same, except they differ in exactly one person's data, right? I can obtain D prime from D by, say, adding or removing one person's data. So we say that an algorithm is epsilon differentially private, where epsilon is some parameter controlling the strength of the guarantee, if we can promise that for every output x, the probability that this thing x actually happens is almost the same whether we run the algorithm on D or on D prime, where almost the same is controlled by this sort of 1 plus epsilon multiplicative factor. Okay, so think about what this means, as if D is the data set that contains your data. D prime is exactly the same data set, except you've opted out of the data set. You decided not to participate in the analysis. And X is some event that you're concerned about. What this is saying is that no matter what thing that you're worried about, it's almost no more likely to occur whether or not you allow your data to be used. Okay. So, one more piece of math here, but this is sort of an important property. If we've got a differentially private algorithm, say M, it's epsilon differentially private, and then we run it and we do something with the output. We think about it. We do some further computation, something that is called post-processing. Then it turns out that this further computation can't make the algorithm any less private. Okay, if you've got an algorithm and you run it and then you think about the outcome and do something else as a function of that outcome, that entire end-to-end process isn't any less private than if you'd just run the algorithm and done nothing else with it. This actually is sort of important in how you can interpret the guarantee, because suppose what I'm doing is I'm running some study. I'm trying to figure out whether smoking and lung cancer are correlated. Well, the output of this thing might be some statistic. Maybe I'm outputting a p-value. I'm deciding whether or not to reject a null hypothesis. Something technical and something that probably you don't have strong opinions about on its own. But there are things you do care about. Okay, and because of this post-processing guarantee, what you can sort of interpret differential privacy as saying is that no matter what event it is you care about, maybe that event is being re-identified in the data set, like in the Netflix challenge example, or maybe the thing that you are worried about is that your health insurance claims are going to be denied, or maybe the thing that you're worried about is that because you provided your data, you're going to start getting annoying telemarketing calls during dinner. Differential privacy can literally promise you for all of these things, for all of these events, whether your health insurance claims are denied or whether you get telemarketing claims during dinner, that you're increasing the likelihood of these events by only a tiny amount in the worst case by allowing your data to be used. Okay, so that's why differential privacy is such a strong guarantee. That's what it's really promising you. Okay. So, it's all well and good to give, strong mathematical guarantees of privacy, but it would be kind of useless unless we could do interesting things with them. Okay, and the strength of differential privacy is that we can. All sorts of, machine learning and data analysis tasks are amenable to being done with differential privacy. Let me just give you a taste of how that might work for the sort of very simplest statistical analysis that you might want to do, which is just computing the average of a bunch of numbers. Okay, so suppose that you want to conduct a survey. Maybe an election's coming up, and you're trying to figure out what fraction of people in the United States are going to vote for the Republican candidate. Okay, so the traditional method of abstracting away an entire field of survey methodology is to just do the following n times. Okay, you pick a person at random. Okay, somehow you pick a random phone number. Maybe you call them up, and then you just ask them who are they going to vote for. Okay, and they tell you some answer, and you write it down in your notebook, and then you sample another person, and you ask them who are they going to vote for. Okay, they tell you some answer, and you write it down in your notebook. Okay, now in the end, all you really cared about was sort of the average of these data points you collected. Okay, you conclude in the end by just tabulating everything and summing it up that maybe the Democrat is expected to get 52% of the vote. Okay, but unfortunately, like, even though this was the only number you cared about, this average, along the way you had to gather all of this potentially sensitive information about particular individuals. Okay, like, you didn't care how, Susie from Indiana was going to vote, but along the way you had to collect that and write it down in order to get access to this average. Okay, which, someone might worry about. Maybe your records are going to be stolen or subpoenaed. But okay, you can sort of tabulate this up, and of course, when you get some average, you don't expect that this number is exactly right. You get some error bars, right, depending on how many people you actually polled. Okay, in general, these error bars, these confidence intervals, shrink at a rate of 1 over the square root of the number of people you sampled. So here's another methodology you could use that is almost as accurate, but is going to guarantee you differential privacy. Okay, so again, I'm going to randomly sample people, but this time I'm not going to ask them to, directly tell me who they're going to vote for. Instead, I ask them to flip a coin. Okay, and maybe I say, if the coin comes up heads, okay, tell me who you voted for. But if the coin comes up tails, give me a random answer. And definitely don't tell me how your coin flip came out. Okay, so maybe they then tell me that they're going to vote for the Republican, and I write that down. But because I've asked them to engage in this coin flipping procedure, that doesn't mean that this person is actually going to vote for the Republican. I don't have the ability to form a very strong belief one way or the other, because okay, half the time they were telling me the correct answer, but the other half of the time, and I don't know which is which, they were just giving me a random answer. Okay, so this person has a very strong degree of plausible deniability, and the information that I write down about each person in my notebook doesn't correlate that well with their actual data. Okay, but sort of the amazing thing is that even though I'm only, getting this sort of very noisy signal about who every individual I called up is going to vote for, because I understand very precisely the process by which the noise is being generated, in particular, like, every time someone tells me something, I know that 3/4 of the time it's who they're actually going to vote for, and 1/4 of the time it's the opposite. It's possible to, in aggregate, unbias the responses, to subtract out most of the noise. In this case, just by taking the average, subtracting off 1/4, and multiplying by 2. Okay. So when I do this, I can again come up with some estimate for the fraction of the vote that in this case the Democrat's going to get. And now, of course, I've got two sources of error in my estimate, right? On the one hand, I still have the same sampling error that I had before, right? Because I didn't ask everyone in the country who they're going to vote for. I just asked some random sample. And now I have another source of error as well, this estimation error, because people are individually flipping coins, and if I get unlucky, all of these coin flips might come out in the wrong direction for me and result in some enormous error. But it turns out that miraculously, the sum of these two errors is on the same order of what just the sampling error was before. Okay, so I can get, by asking people to follow this randomized response procedure, a very accurate estimate, almost as accurate as I got without the need for randomization, without asking people to flip coins, a very accurate estimate of the statistic that I ultimately wanted to compute, without ever having to directly collect individuals' data. Okay, so it turns out that, as I've described it, this computation is too differentially private, and of course, I could modify it to modulate this privacy parameter, right? If I decrease the chance that you give me a random answer in the protocol, the privacy protections will get weaker, the privacy parameter will get bigger. And if I increase the probability that you respond with a random answer, the privacy protections will get better, the privacy parameter will get smaller. Okay, so there's some trade-off here between privacy and accuracy, but the end result is that I'm able to still get the thing that I wanted, this population-wide statistic, while giving every person who participated in my poll a very strong guarantee of plausible deniability. You know, if you are in the future subpoenaed and you know, asked, you know, did you vote for the Republican? It says in this record that we have that you did. You can plausibly say, well, no, I didn't. When I was asked that question, the way the coin flip came out was that I was told to provide a, you know, a random answer. Okay, so this is maybe the most basic example of the sort of computation that you can usefully do subject to differential privacy. But you know, essentially any learning or data analysis task you can think of can be solved subject to the protections of differential privacy. Okay, so this includes almost all of machine learning, you know, both sort of, you know, maybe old-fashioned by now convex learning, things like support vector machines and logistic regression, but more generally anything that you can do with, for example, stochastic gradient descent. So this includes, you know, most of modern deep learning. You can do, you know, spectral analysis, singular value decomposition, principal component analysis, things like this, and as well as sort of more classical, you know, statistics, things like hypothesis testing. Okay, and for all of these tasks, the strength of differential privacy is that it allows us to sort of through this privacy parameter, you know, precisely quantify and manage the privacy risk through this privacy parameter epsilon and trade that off with things like accuracy. So in general, there is an inevitable trade-off between privacy and accuracy as you sort of drive the privacy parameter to 0, which corresponds to perfect privacy. You know, the extent to which you can solve any of these problems, you know, becomes trivial. You can't solve any of them if you don't look at the data at all. And similarly, as you drive the privacy parameter to infinity, the constraint becomes vacuous. You can solve all of these problems as well as you could without any privacy guarantees. And the nice thing about this parameter is it lets you now precisely and formally reason about and trade off different things you might care about, in this case, privacy and accuracy. Okay. So this is most of sort of what I want to say about differential privacy today. Differential privacy is, at this point, a very mature field, and there's, you know, a lot more you can learn about it if you're interested. I'll give you some pointers at the end of the talk. But for about a decade, it was, you know, maybe an academic curiosity, the sort of thing we would write obscure papers about. But in the last few years, we've seen sort of real technology transfer from academia to industry and several large-scale deployments. Okay, so if you use the Google Chrome browser, then reporting statistics for various aspects of your use are sent back to Google using a variant of this randomized response protocol. Similarly, if you have an iPhone, iOS 10 does its data collection subject to differential privacy. That was a project that I was a consultant on. And sort of maybe, you know, most amazingly, because, you know, normally we think about government as being a lot slower to adopt new technologies than industry, the US Census Bureau has embraced differential privacy, and all of the statistics released as part of the 2020 US Census are going to be released subject to differential privacy. Okay, so this is a real success story. If you look at what's happened over, you know, the last 10 or 15 years, we went from sort of not being able to do anything other than add sort of ad hoc privacy protections that we sort of crossed our fingers and hoped would work and found often that they didn't, to having a real, you know, mathematical science for how to think about privacy and machine learning, to having, you know, serious large-scale deployments. Okay, and the real turning point, I think, and this is something that I want to emphasize as I go on to the next part of the talk about fairness, the real turning point was deciding to think about the problem precisely, to precisely define and quantify what exactly we meant by privacy. Okay, once we were able to rigorously do this, then we made rapid progress in designing algorithms that could do the thing that we wanted. Okay, and that's going to be part of the challenge over the next, say, decade as we grapple with how to think about fairness in machine learning. Okay, so let's now switch gears and talk about fairness. And I want to begin by talking about it in exactly the same way that we talked about privacy. Okay, so with anecdotes. So, if you've been following the popular media over the last, few years, you've probably seen a number of articles that look like this, that are sort of worrying and hand-wringing that, as we start using machine learning, not just for, spam filtering and which ads to show to different people, but for, for decisions that really affect people's lives, like who goes to jail and who gets loans and who gets hired, that the blind use of these techniques provides some, maybe veneer of unbiasedness, but that what's actually going on is that maybe, these algorithms are perpetuating and exacerbating inequalities that, have always existed in our societies. Okay, so you've probably come across, lots of these articles if you've been paying attention. There's no shortage of them. So a very natural reaction when you first hear this is to say, okay, well, let's not be crazy. What do you mean that an algorithm is unfair? An algorithm is this dispassionate thing that is, generally in machine learning, just, like looking at the data and directly optimizing some entirely unobjectionable, cost function, like it's trying to minimize its classification error. How can that be unfair? Okay, and so it's tempting to say that, people who worry about this just don't understand, how algorithms work, and that, what a machine learning algorithm is going to do is just, uncover patterns that already exist in the data, and, if you don't like the outcome, then the problem's not with the algorithm, the problem is with the data. Okay, so that's a very natural thing to think, and it's a natural first reaction, but it's wrong. So the first thing I want to do is go through just a toy example to convince you that that's wrong. Okay, so here's a toy example. Let's think about a lending application. Okay, so suppose that I'm trying to, from some big data set, learn a simple rule to determine whether people are going to pay back their loans or not. Okay, and suppose I've got two different populations, a majority population that's colored green and a minority population that's colored orange. Right now, you're just seeing the green points. Okay, and for the sake of argument, let's imagine that I've got like two numeric valued features about individuals in this data set. Let's call them SAT score and the number of credit cards they have, although it's a cartoon, so what these features are really doesn't matter. Okay, so I'm showing you the green points right now, and I want you to, staring at this cartoon, notice a couple of things. So first of all, slightly fewer than half of the green points are creditworthy. Let's say that the pluses in this diagram are the positive examples, the people who ultimately do pay back their loans, and the minuses are the negative examples. So slightly fewer than half of the examples are pluses. That's the first thing to notice. The second thing is that it's pretty easy to give at least a sort of rough rule to determine who's going to pay back their loans and who's not. If you look at the data, there's a linear separator. There's a line I can draw through it. So something I'd get from, say, logistic regression or training a support vector machine that can pretty accurately classify these points, although not perfectly. Okay, so these are the green points. Now I'm going to show you the orange points. So here's the orange points. There's a couple of things you might immediately notice. Maybe the most salient of which is that there's fewer orange points. That's by definition, right? Like the green population is the majority population. The orange population is the minority population. What that means is that I've got less data about the orange people. Maybe the second thing you'll notice is that the SAT scores of the orange population are sort of uniformly lower than they are for the green population. That is, on this plot, all of the points are shifted downwards. Okay, who knows why, but maybe the green population is wealthy and takes SAT tutoring classes and takes the SAT 5 times and only reports the highest score, and the orange population, just takes it cold once and sends their score in. It doesn't matter, but whatever the reason is, the orange population has uniformly lower SAT scores. Now, note, however, that if we're the bank, like SAT scores aren't what we care about. What we care about is whether people pay back their loans. And from that perspective, the orange population is actually better than the green population. I remember in the green population, slightly fewer than half of the individuals paid back their loans. Well, in the orange population, exactly half of them pay back their loans. So on average, the orange population is actually more creditworthy than the green population. And it's also easier to tell in the orange population who's going to pay back their loans. In the green population, there was a linear separator that, did a pretty good job, but not a perfect job of distinguishing the positive and the negative examples. But in the orange population, we've actually got a linear separator that can, get perfect classification accuracy. Okay, so the, orange population is both more creditworthy on average than the green population, and it's easier to tell who's creditworthy and who's not. Okay? But now let's look at what happens when both of the points are combined. And let's say that the algorithm is not allowed to look at race. Okay, so it can't see the colors of the points. All it can see are the SAT score and the number of credit cards. This is, by the way, in lending, legally mandated. You're not allowed to make lending decisions as a function of race. So suppose I do the sort of extremely sensible sounding thing of taking this data set and just finding the linear separator that minimizes classification accuracy. All right, think for a second about what's going to happen. What's going to happen is that I'm just going to find the linear separator that best classifies the green population. Okay, that's for a simple reason, which is just that there are more people in the green population. If I shifted down my classification region to try to get better accuracy to better fit the orange population, well, I could increase my accuracy on the orange population, but it wouldn't be worth the decrease in accuracy I had for the green population, for the simple reason that there's more green points, and that the fraction of errors I make on the green population therefore contributes more to my overall error rate. Okay, so I did the completely reasonable sounding thing of just taking this data and finding the linear separator that best classifies the points on average. And what I got was a rule that, denies loans to all orange people. And this was not because the orange people were not creditworthy. In fact, the orange people were more creditworthy on average than the green people, and it was easier to tell them apart. This was just because when I've got two populations with different statistical properties, and I minimize my average error, then what will inevitably happen is I'll just fit the majority population. Note, by the way, that in this example, if I were allowed to use race in my decision making, I could have learned a much better rule. I could learn a separate rule for green people and for orange people, and I would have increased my accuracy, and also I would have increased my fairness, whatever I might mean by that, for just about any reasonable definition of fairness. Okay, so the upshot of this is that, although of course algorithms are dispassionate, if you just do standard things, like optimize for accuracy alone, and you've got two populations that differ in their statistical properties. They differ in what is the best classification rule for that population alone. You're going to end up doing something that might look unfair, because what you'll end up doing is just fitting for the majority population. Okay, the other takeaway is the slightly counterintuitive fact that whatever you mean by fair, we'll go into this in just a minute. In order to achieve it, it might be necessary to explicitly use race as a variable in your prediction problem, even though maybe your first gut reaction is to try to be fair by making sure your algorithm doesn't get to look at race. Okay, so we can see that natural things can be unfair, whatever that means. What I want to do is think a little bit now about what we might mean by fairness. Okay, unlike in the case of privacy, there's not a single agreed upon definition, but we've got a couple of reasonable ones. At a high level, by the way, I would say that the sort of literature on fairness in machine learning at the moment divides equally between what I would call individual definitions of fairness and what I would call statistical definitions of fairness. And at a high level, individual definitions of fairness ask for sort of nice semantically meaningful constraints that bind on individuals. They say that similar individuals should be treated similarly, or that you shouldn't preferentially give loans to less qualified individuals over more qualified individuals because of something like their race. Okay, these are nice definitions, but the problem has been that they're often difficult to put into practice. And so what I'm going to talk about in the next 10 minutes are these statistical fairness notions. There's a bunch of them, but they usually take the following form. Okay, so you can partition the world into some small number of protected subpopulations. Often it's just 2. So think about these as divisions of the population by race or by gender. Okay, and once you've got these protected groups, say men and women, you just pick your favorite statistical property of a classifier and ask that it be the same on the 2 groups. So for example, I could ask that the rate of positive classification is the same on 2 groups. The fraction of men who get loans should be the same as the fraction of women. Or I could ask that the classifier doesn't make substantially more errors of one kind on one population than another. I could ask that the false positive rate on men is the same as it is on women. Or I could ask that the positive predictive value be the same for men and for women. For example, what this means is that the classifier should sort of mean what it says. Given that I decide to give a man a loan, the probability that they end up paying it back should be the same as it is for a random woman that I decide to give a loan. Okay, these are all sensible sounding definitions. But you can't have it all, unfortunately. And so there's an informative case study that some of you might have heard about that I'll describe to you now in cartoon form. Okay, so it turns out one of the controversial uses of machine learning is in recidivism prediction. So in various jurisdictions, including in Florida, if you are convicted of a crime and are then up for parole, the judge in your parole hearing will have access to the prediction of a proprietary model that's trying to look at data about you and predict whether you're going to go on to commit another crime or not if you're released. Okay, so at a cartoon level, people have features, and in our data set, maybe they've got some label like when they were released, they really did go on to reoffend or not, and the tool's just trying to solve a binary classification problem like this. So ProPublica got a bunch of data about a particular one of these tools called Compass, and they wrote a highly publicized article insisting that the tool was unfair. And what they meant by that was that it had a higher false positive rate on the Black population compared to the white population. Okay, so if I looked at people who actually did not go on to reoffend, the algorithm was more likely to falsely accuse Black people who did not go on to reoffend of being at high risk compared to the rate at which it falsely accused white people. That's bad. Now, North Point wrote a pretty detailed response in which they asserted that in fact their tool was fair, but they had a different definition of fair. What they meant is that the tool had equal positive predictive value, meaning that given that the tool predicted that a Black person would reoffend, the chance that they actually went on to reoffend was exactly the same as the chance that a random white person went on to reoffend, conditioned on being labeled as high risk. Okay, so that the tool meant what it said, independent of race. That's also a desirable property. Okay, so both of these organizations, ProPublica and North Point were thinking about fairness differently. Okay, they defined, the same protected groups, in this case black people and white people, but they had different definitions of fairness. ProPublica was asking that the tool be equally well calibrated on both groups, and North Point was asking that the tool be equally well calibrated, and ProPublica was asking that the false positive rates be equal. Okay. Well, it turned out they were talking past each other, because as it turns out, no classifier can simultaneously satisfy both of these conditions under realistic circumstances. Okay, so as it turns out, you can't have it all. You can't even satisfy multiple reasonable sounding fairness definitions. And so just as in privacy, when we had to manage trade-offs between the privacy level quantified by epsilon and the accuracy rate, when we talk about fairness, we have to manage trade-offs even between different fairness definitions. So let's dig a little bit further here. Let's pick one of these fairness definitions, as this impossibility result obligates us to do, and ask whether it's even a sensible definition. Like, why should equalizing false positive rates between black people and white people correspond to anything we mean by the English word fairness? Okay, so here's a little thought experiment. Suppose that you know that you are actually low risk. If you are released, you are not going to go on to commit another crime. Okay? Well, if you think of yourself as a uniformly random member of your population, then the false positive rate is exactly the probability that the algorithm is going to wrong you. It's the probability that the algorithm is going to incorrectly label you as high risk and therefore lead to your further incarceration. Okay, so if the false positive rates are different for the two groups, then all else being equal, you have a good reason to sort of want to be born as a member of one of these groups as opposed to a member of the other. Okay, or equivalently, if I can promise you that the false positive rate is equal for these two groups, then behind the veil of ignorance before you're born, if you think you're going to be born as a uniformly random, low-risk member of one of the two populations, you should be indifferent between which race you're born as, which is a nice semantics for fairness. Okay, but in this thought experiment, it's actually pretty important that you believe you're going to be born as a uniformly random member of one of these populations. Okay, and because of that, these group fairness definitions don't really have, aren't really very meaningful when it comes to what they promise to particular individuals. Here's a toy example. So suppose that I've got 4 protected groups. Okay, maybe you've got some gender and some race, which we'll refer to as men and women and blue and green. Okay, and let's suppose that the label we're trying to predict, maybe whether or not you're going to go on to commit a crime, is actually independent of both your gender and your race. Okay, so if you ask me to design a fair classifier, maybe you want me to equalize the false positive rate among men and among women and among blue people and among green people, okay, that sounds sensible, but one way that I might accomplish that is by deciding to jail all blue men and all green women. Okay, so this turns out to equalize the false positive rate among men, among women, among blue people, and among green people, but this is little comfort to you if you turn out to be a blue man. Okay, the point was that you're satisfying this constraint on average over these big coarsely defined groups, but if you happen to know that you are not a uniformly random man, but that you're a blue man, this is really promising you nothing. So at a high level, the problem here is that these statistical constraints, which are defined just as these, averages over these sort of broad groups, can be sort of gerrymandered, if you like, to pack the unfairness into structured subgroups. And this isn't just something that happens, in like a toy example you can cook up. As we'll see in a minute, this is something that actually does happen when you run standard optimization techniques. Okay, so let me just briefly tell you a simple sounding, although technically interesting, mitigation of this problem. Okay, you might think that the problem was, well, you know, I just didn't include enough groups in my protections. I should have explicitly asked for blue men and green women to be protected, and I could have. But then, you know, what about other groups? Okay, and it's sort of easy to see that there's no way to promise protections like this against all groups you could define, you know, ex post, because unless I come up with a perfect classifier, you could always accuse me of being unfair to exactly the group of people that I made mistakes on. Okay. In other words, I'd sort of expect to just be like overfitting your fairness constraint. But as it turns out, it still makes sense as a statistical problem to ask for these statistical fairness constraints, not just over you know, a small number of coarsely defined groups like Black people and white people, but over exponentially many or even infinitely many groups that could be defined as, say, the ands of any, you know, subset of the protected attributes. Maybe, you know, I can separately ask for fairness on, you know, Black disabled women and, you know, Hispanic men over the age of 65, right? So you can define a problem like this, and it turns out that you can efficiently solve this problem, find the most accurate classifier subject to satisfying a statistical fairness constraint, like equalizing false positive rates, over any subgroup that can be sort of defined by some class of functions G, like all of the ands of protected features that you might take. And that you can simulate a zero-sum game, if you like, between a learning player who's trying to you know, find an accurate classifier and an auditor who's trying to find a subgroup on who the learning player is discriminating. Okay, so you know, forget the details, but suffice it to say that you know, if you do things correctly, and I'll give you a reference at the end, you can get an algorithm that really works. Okay, what you're seeing here is the trajectory of the classifiers learned by an algorithm in which the x-axis is denoting the accuracy of the classifier learned, and the y-axis is a measure of the unfairness as measured by the difference in false positive rates over exponentially many different groups. And what you're watching is the convergence of this to the most accurate classifier that satisfies a target fairness level. Okay. Once you've got an algorithm like this, you can start to ask quantitative questions about trade-offs. For a variety of different data sets, you can ask, you know, like, what is the cost in terms of my accuracy of increasing the sort of fairness level, according to my favorite definition of fairness, by a little bit? And what these trade-off curves look like, what these Pareto curves look like, are different on every data set. But what you often find is that you can get, you know, pretty big increases in fairness for only mild decreases in accuracy. And you can make other pretty pictures to watch the convergence. Okay, so I'm out of time. I just want to summarize a couple of things. First of all, scientific progress is driven in large part by precise definitions. And even though when we're thinking about sort of ethical and social issues, things like privacy and fairness, it can be difficult to capture a lot of what we mean mathematically, it's still worth trying. Because when we succeed, we can, you know, give formal guarantees, we can plainly see how to design algorithms that satisfy these definitions, and we can understand and manage the inevitable trade-offs that arise. Okay? And privacy here is a success story. This is an approach that works. Okay, and we have at least one good example. And fairness, it's a work in progress, but I think there's good reason to want to take this precise formal approach and push it as far as it goes. All right, so here's some information if you wanna learn more. You can follow me on Twitter. I occasionally tweet about this stuff. I've got a textbook on differential privacy that well, you could either spend a lot of money on, or there's a PDF of it for free on my website you can download. The fairness gerrymandering work is from a paper that appeared in ICML, this most recent edition, and together with Michael Kearns, I'm writing a popular treatment about a lot of this stuff that I hope you'll enjoy reading. It's called The Ethical Algorithm, and it's going to be published in 2019. So with that, I'll be happy to take some questions. Give me a